Hello and welcome to the lecture video accompanying lecture 26. In this video we are going to discuss sections 28 through 28.7 of Survey 11th edition covering the topic of atomic physics. We are primarily going to focus on the Bohr model. If you haven't already, please go back and check out and watch the 3 accompanying videos for lecture 25 where I go over slides that show diagrams, introduce the concepts, as well as touch on the key formulas for this topic of atomic physics. Okay, in this video and this lecture, we're going to focus on the equations, exactly what the equations are, and then put them to use in some simple numerical examples. Okay, I also want to point out that there will just be a single lecture video for lecture 26, so we're going to get through all the notes. It's not very lengthy, and the concepts are related enough that it makes sense to do one video. Okay, so let's take a look at our objectives. So we want to understand that the Bohr model allows us to calculate energy levels of electrons in allowed states with the principal quantum number, and that principal quantum number is going to be represented by n. It is an integer. We are further going to understand that the Bohr model allows us to calculate the radii and velocities of electrons in those allowed energy states, those quasi-orbits. We're going to realize that the Bohr model can be extended to work for ionized atoms that become hydrogen-like. Okay, so a hydrogen-like atom is an atom that has how many electrons? 1, right? 1 electron is a hydrogen-like atom. And it turns out that the Bohr model really only works well for hydrogen-like atoms. But that said, there's one other practical use of the Bohr model, and that is to see that the Bohr model can be further extended to estimate, right, key being estimate here, the energy levels of characteristic X-rays of emitted by larger atoms when an electron in the K shell is displaced. Okay, so the idea there is that that inner shell is still sort of hydrogen-like, and we can discuss its properties and its energy levels in a way that is uses a lot of the same ideas of the Bohr model. Okay. Now again, a lot of the theories I'm not going to be covering, but I do want to touch on them as I go through the key formulas, which we're going to start right now. Okay, so our first key formula is kind of really something we've seen before, and this just has to do with the energy of a photon and how it relates to the energy levels of an atom. Okay, so let's go ahead and label some things here. So this is the energy level of a photon. E for a photon, and the idea here is that light coming in, thought of as the individual energies of photons, can cause electrons in atoms to be excited, and when those electrons within an atom are excited, the energy difference that's represented by that excitation is our delta E. Okay, so this is delta E of the electron in the atom, okay? And that's the idea of the energy states of that electron, okay, which we can think of pictorially in a cartoonish way as orbits, all right? I here is just initial, the F is final, okay? The N is the principal quantum number. So principal, and that's the only quantum number that we are going to be discussing in this video. If you want further practice with the other quantum numbers, L for the orbital quantum number, M for the orbital magnetic quantum number, and S for the spin quantum number, please take a look at lecture 25, watch those videos, go over the notes with the slides, read the textbook, okay? And those are ideas that you're responsible for, but those are conceptual ideas, they're not numerical. And so in this lecture, focusing on numerical examples like you would see in the computation section of the exam, that's what we're doing, right? You would not see any problems involving other quantum numbers in the numerical section of the exam, okay? So principal quantum number, and then n can be any integer greater than 1. Okay, all right, so hopefully that makes sense. All right, so that's good place to start because we're going to be talking a lot about excitation of electrons, and we're often going to relate that to maybe the wavelength of the light that caused the excitation, or perhaps the wavelength of the light that was released when the excitation was over and the electron relaxed to its ground state or to a lower energy state. All right? Well, the other big thing that we want to discuss in the Bohr model is the idea of having the de Broglie wavelength. All right? And that's what's represented here, is that there has to be an integer number of electron de Broglie wavelengths that fit in any given orbit. Okay. And again, there's a slide that shows this. I can't really draw it to do it justice here, and that would be a slide in lecture 25. But here I'll just point out that what this states is there must be an integer number of electron wavelengths that fit, kind of a general term there, that fit in any electron orbit. Okay, so what's going on there? Well, the idea is that you can't have a half wavelength in a given electron quote-unquote orbit. I try to call them energy states, but here I want to call them orbits because just like orbits, these electron energy states have a quantifiable expression. And it turns out that it's not perfect, right? The Bohr model isn't perfect, but it represents the radius of that orbit. Okay? So that's what R is. This is the radius of the nth energy state. In other words, the nth orbit. So radius of nth energy state. Okay, and by energy state, I mean orbit. Okay, so again, please make sure you understand that concept. Take a look at lecture 25, right? And as I say in the video, it turns out that the idea of having de Broglie wavelengths fit within the energy states of the hydrogen atom actually historically comes later. Bohr at the time thought of it as quantifying the angular momentum because of the work done by Planck and the idea of black body radiation. But it turns out those ideas are consistent and perhaps better understood as fitting full wavelengths within a circular orbit. All right? The important thing here, and I'd say a good thing that to make sure you're getting a handle on, is that this lambda is the wavelength of what? Well, since it's equivalent to the energy of the photon, it is the energy of, or it's the wavelength, excuse me, of the photon. Now I'm going to go ahead and label that because of the importance of the, okay, so this is photon wavelength. The importance of just keeping our terms consistent and clearly expressed. Whereas here, what is this? Well, this is definitely not the photon wavelength. This is the electron wavelength. Okay, so important distinction there. Now, is the electron wavelength going to show up ever again as we go down through these equations? Graciously not, and importantly not, because we really wouldn't be well suited to doing expressions where we're going to be solving all this stuff, talking about it all in terms of the electron wavelengths, and then relating it to the photon wavelengths when we don't have to. Because what we can do is we can express the electron wavelength in terms of the mass and velocity of the electron and leave it there and have those be the terms, the classification, the way of quantifying our electrons that we use, that then we can relate back to the light that is either being emitted or absorbed by our atom. Okay, so much more direct, or so much less confusing, right? rather than, because ultimately it is waves and waves. And if you want to get down to the beautiful ideas of quantum mechanics, then that is crucial. But it also is unnecessarily confusing, okay? So we're going then to take that electron wavelength and never see it again, okay? So we're going to set the electron wavelength equal to, for all future purposes, Planck's constant, mass of the electron, velocity of the electron in a given orbit. Actually, let me add, I'm trying to put an N on all the V's. I left this one off, okay? And more labels, okay? So that's the same electron wavelength. We have N is still the principal number, so nothing new there. H we've already seen, but I actually want this to be pretty kind of standalone. C is the speed of light. No surprise there at all. And I'm going up to the line above just to fill in things I hadn't labeled. H is Planck's constant. Okay. Make sure. Anyway, all right. So, okay, so Planck's constant. M is the mass of the electron, because that's, when we're talking about these atoms, we're talking about their electrons here. When we talk about their nuclei, that's going to be a later chapter, the next chapter. So mass of the electron, okay? And then this is the velocity of the electron in a given energy state, okay? And I was going to say quantum energy state, and they are quantized because, of course, we're talking about the principal quantum number, which I left off the word number. But it's not, we're not using all of quantum mechanics, right? So we use quantum here in a sort of light way. Okay, so this is the velocity of electron in energy state. Okay, so the subscript there is telling us that it's in the nth energy state. Right, so I'll go ahead and put that same terminology in nth energy state, okay, which would be an orbit. Right, so quick idea here. This is our electron. It's moving at some velocity. It's moving in an orbit that has a radius, okay? So those sound like classical ideas, okay? But remember that this is Bohr having his cake and eating it too. Okay, which happens sometimes when theoretical physicists are trying to make things work. Because the reason that I say that it's Bohr having his cake and eating it too is because he's using ideas of classical physics while ignoring ideas of classical physics. In other words, he has classical mechanics to have an orbit. He's using those classical mechanics and using some quantum mechanics to give an appropriate wavelength based on the momentum, because of course down here, I don't have too many things circled, but down here is the momentum of that quote-unquote classically orbiting electron, right? And of course then Planck's constant divided by momentum, according to Broglie, is the wavelength, or the matter wavelength, right? It's a matter wave. The electron is a matter wave, okay, with a certain amount of uncertainty. Okay, but I don't want to get off topic here. What's the classical physics that Bohr is ignoring? Well, Maxwell's equations, okay? All of the idea of electromagnetic radiation. Because if this electron is truly in an orbit with a certain velocity that is not changing in magnitude, so constant speed, well, that's uniform circular motion. With uniform circular motion, there's an acceleration. Sure, there's no tangential acceleration, but there's still a radial or so-called centripetal acceleration. Well, there you go. That's an acceleration. And anytime you have an accelerating charge, like an electron, right, which has fundamental charge, what do you get? You get a changing electric field, which creates a changing magnetic field, which creates an electromagnetic wave, which is a photon, as we know. And what do photons carry? Energy, which means this orbiting electron would have to be emitting energy. But right away, Bohr realized that couldn't be the case because atoms would be fundamentally unstable, and they're not. So the electron's not radiating away energy, but yet it's still orbiting. Right? See? It's like when you can't choose, you just take them both. Okay? So this is the quantum side of the Bohr model. And down here, it's summarized again. What have we done with this summarizing? Well, I took the idea of lambda, right? Because if you can express lambda according to the Broglie as h over momentum, okay, Planck's constant over momentum. And then you can also take the Bohr's quantifying of the energy states and saying that there has to be a full wavelength that fits in each circular orbital radius. And when you set the two lambdas equal to each other, so I take here, I'd have 2 pi divided by n, right? And so then when I set lambda equal to lambda, then what we get is then we just get this expression right here, all right? So this is just, and then and we did some cross multiplication, okay? So this is essentially what this line is just showing, is that we can eliminate the electron wavelength from our expressions. So let's show that. So this simply shows, here I'm going to put this, because it's not a label, I'll put it in black. So shows that we can eliminate electron wavelength from our equations. Okay? Now we could go back and solve for it, sure. But if we don't need to, we're not going to. All right? If we're not explicitly asked to. All right, so nothing new here, just showing kind of intermediate step of algebra. And we'll come back to why that's important. Now, back to Bohr and the model, right? So we've got the quantum side of Bohr's model. Here is definitely the classical side, right? Again, the classical side he chose, the mechanical side, while ignoring the Maxwell's equation side of his classical formula, all right? Or expression, or formulation, whatever you want. Here it is, right? This is just the net force on the electron of the hydrogen atom. Okay, so when I say F hydrogen, this is F for force. So this is the net force acting on the single electron. That's important that there's a single electron of hydrogen atom. Okay, now like in the post quiz I gave you, that it will be due as in a take-home format on Thursday. Just answer the 4 questions, or the 4 parts of the single question. In that case, you have the one other time that the Bohr model works fairly well, which is for helium. And in that case, the only thing that's different about helium is you've got a different net force, because then you have the attractive force of the nucleus, which would show up from this, which is Coulomb's law, and then you have the repulsive force of the other electron, which you're told to assume is on the far side of the radius, so it would be twice as far away as the nucleus. All right? And when you do that, that's going to be your sum of forces, and then everything else is going to fall from there. You're still going to have the same quantization of the energy levels in terms of the de Broglie wavelength. That part is completely unchanged. Okay? I mean, the velocities change, but the idea that the electrons are matter waves and have a wavelength equal to Planck's constant over the momentum, that part is exactly the same. All right, so what is the net force, right? What does it tell us? Well, there's only a single force acting on the quote-unquote orbiting electron, and that is the attractive Coulomb force, right? So this would be the charge of the nucleus. Nucleus charge, which is positive, and then this is the electron charge. Both have the same magnitude. They both have a value of E, the fundamental charge, 1.602 times 10 to the negative 19 coulombs. Okay, that's the charge of an electron, also the charge of a proton. All right, and so that's what we're seeing here, because the nucleus is a single proton and the electron is just that, an electron. All right, and Coulomb's law always has the coefficient in front, sometimes called the electrostatic coefficient, represented by K sub E, but here 1 over 4 pi times the permittivity constant, which I'll label just in case you've forgotten it. Okay, and I'll be writing out the numerical values of all these constants in a second. So permittivity constant. All right, and then of course since it's the Coulomb force, and the Coulomb force is inversely proportional to the distance between the charges squared, then that's what we're seeing here. This is the distance between the charges squared. So this is just the radius of the nth orbital state, or energy state, okay? All right, so this cleans up as just E squared, all right? Everything else we already know, okay? Now, here's the thing. Since this is the only external force acting on the electron, but the electron definitely is not at rest, it's accelerating, Newton's second law tells us that this single external force must be equal to mass times acceleration. And here, the only acceleration is centripetal acceleration. Okay, so this is just Newton's second law. That's the equal sign here. Just F net equals ma. All right, and then AC is just centripetal acceleration. All right, and centripetal acceleration always takes the form of v squared over r, which is exactly what it has done here. But here it's the velocity of the nth orbital state and energy state, keep wanting to call it orbital state, and it's the radius of the nth orbit, which is the nth energy state. Okay? So from this net force equation, we can immediately express the nth orbital radius and the nth velocity, again, nth energy state for both cases, in terms of just E, principal quantum number, and Planck's constant, okay? For the radius, we have the mass of the electron show up, all right? All right, I'm trying to, so yeah, and then the other thing is I didn't realize I left off the subscript E a couple of times. So every time you see an M, it's the mass of the electron. I meant to put it on every single one, but it obviously got dropped a couple of times. So all the M's should be M sub E's. They're all the same M. It's the mass of the electron. All right? And so, just taking a look at one thing. So the way, let's see, the way that we make this relationship is, so if we think about it, this allows us to solve, so we could take this expression, right? We could take, I'll show you what I'm looking at here. I'm going to circle it in a different color. So we take this expression right here, because again, that's just Newton's second law, all right? And then I could express, for example, this one. I could express Rn in terms of E, permittivity constant, pi, mass, and, right, and I'd cross multiply by R, right? So I'd have, one of them would cancel, right? And then I'd also express it in terms of V, okay? But notice V doesn't show up in this expression. Why is that? Well, because I've substituted out V in terms of R based on that expression. So that's where they come together. That's where we're taking the ideas of fitting de Broglie wavelengths and an integer number of those de Broglie wavelengths in a given circular orbit, and then combining that with Newton's second law and centripetal acceleration. Okay? So what I want to show then is what that looks like then. So we would say, if we call this equation 1, actually call this one equation 1, and we call this one equation 2, then we can clearly say then that these two come from combining, these two equations here come from combining 1 and 2. That's all you need to do. Right? There's no hidden steps there. Oops. There we go. So this would be from combining 1 and 2. Equations 1 and 2. Let's make this black. Okay? All right. So there you have it. Radius of the nth energy state, right, which means it must be in orbit, and velocity of the electron in the nth orbital state, which means the electron must be moving. Both of which are kind of wishy-washy ideas, but hey, they work, they're okay, you know, they get the job done. Now, probably more real is then the energy. Okay, so now that we've gotten out of the way the Broglie wavelengths and the whole quasi-classical orbital thing, let's then get to the energy states. Okay, because the principal quantum number, after all, is pretty much about the energy states. So let's cut to the chase. Let's get to the main point. All right. So E sub n, uppercase E, is the energy state of the nth energy state. Okay, it's just the nth energy state. Nth energy state. Okay, now since this is the energy of this electron bound to the nucleus, right, in a stable hydrogen atom, then that energy state consists of kinetic energy and potential energy. All right, so the kinetic energy of our electron is just 1/2 mv squared. All right, is it relativistic? Well, it turns out that it actually kind of is, although it's less than 1% the speed of light, well less. But is it still sort of relativistic? Yeah, that's where the whole Dirac equation comes from and the discovery of spin, right? But of course, that's not something that we can get into in depth in this class. But it's certainly here we can just treat it as classical. All right, so we just have classical kinetic energy. And then we've got the potential energy. The potential energy is the potential energy that's associated with Coulomb force. Okay, so again, we've seen this before. This would be like the work done to move a charge within an electric field. Okay. All right. So why is the potential energy negative? Okay. Well, because potential energy for bound electrons is always negative. It is in a potential energy well, right? Just like the moon orbiting Earth is in a gravitational potential energy well. The electron orbiting the positively charged nucleus is in an electrostatic energy well. Electrostatic because the whole atom isn't moving, right? Even though the electron is, sort of, right? So that's the idea. That's why our potential energy is negative. Okay. When we look at the total energy of the nth state, we get also a negative value. Why is it a negative value? Because if it was greater than a negative value, then that would mean our electron isn't bound to the nucleus at all. Okay, that would be an ionized atom. And in fact, ionization with just enough energy to ionize the electron will give us a final energy value of 0. Because in that case, the electron had just enough kinetic energy to completely escape the potential energy well. Now, you could have excess energy, in which case the electron escaped and is still, has some leftover kinetic energy. But the point being that wouldn't be an atom anymore, okay? That would just be an ionized nucleus. It would just be a proton by itself, okay? In the case of hydrogen. All right, so that's the total energy is negative, the potential energy is negative. And again, the total energy has to be negative because there's no way the kinetic energy can be bigger than the potential, because it's got to still be bound, right? It's got to still be within that well. Okay, so our total energy is negative. Let's make a note of that. Why not? All right, so I'll say total energy is negative because the quote-unquote orbiting electron is still in a potential energy well. It is bound to the nucleus. All right, there. All right, are there any new variables here? Nope, we still have our principal quantum number n, we still got our mass of the electron, we still have our charge of the electron, permittivity constant, right? Nothing new. Planck's constant, all the same variables. All right, one thing we can do is we can take that energy level of the nth state and express it in terms of the radius. That's all I've done here is I've just substituted in the expression for the radius, right? Which cleared up some of the expressions, all right? And in doing so, we can clearly see that as the radius gets larger, the energy gets smaller because it's approaching zero. Okay, it's approaching zero at ionization when the nucleus loses that electron completely. Okay, so that's kind of bringing all the ideas together. And again, energy states are primarily what we're going to look at. All right, although we might be asked about radii and velocities as well, depending on the question. Okay, now one other particular radius we can talk about is the ground state radius. And we express that as a sub naught. I'm not sure why it's a, but it always is. Okay, so this is the ground state radius. And all the radii, by the way, would be measured in meters. They are physical distances. So ground state radius. And the nice thing about expressing the ground state radius, sometimes called the Bohr radius, is that then we can express all subsequent radii as just the principal quantum number squared times the ground state radius. So when we see that the radii, that the nth, n equals 2, so the second state, which would be the first excited state, has a radius that is how many times bigger than the ground state radius? Well, 4 times bigger, all right? And so since the radius is 4 times bigger, that means that our energy is 1/4 as negative, right? So the magnitude of the energy is 1/4 as much. We're that much closer to zero energy, full ionization, okay? All right, which you can see here because, of course, energy is inversely proportional to n squared. All right, and then we can also express the nth energy state in terms of R, okay? Well, what is R? R is the Rydberg number. And the reason we might express things in terms of the Rydberg number, historically, because that was an empirical fitting constant that was discovered through experimentation before the Bohr model, well before the Bohr model was theorized. And it's got that historical distinction. And furthermore, it's kind of a clean way of expressing things. And it's directly related, due to its discovery, to the wavelengths of emitted light, as well as absorbed light, by atoms, particularly hydrogen atoms, right? So like in a hydrogen gas, there's these particular colors that either get emitted or absorbed, and those fall into the series of colors, like the Balmer series and the Paschen series and the Lyman series, and all those series have that constant, the Rydberg constant, in their expression, okay? And then we can directly relate that constant back to the Bohr model, because that's the whole idea, is the Bohr model was designed to satisfy those discoveries, those experimental discoveries, such as the Balmer series. Okay? All right, and a final way of talking about the energy states of those bound energy states, thus negative, of the hydrogen atom is to talk about them in terms of, well, multiples of the ground state. And the ground state has a numerical value of 13.6 electron volts. Okay? So we can say with E1 equaling negative 13.6 electron volts, the energy of the ground state. The energy of the ground state, because you can't go any lower than n equals 1. These electrons cannot crash into the proton nucleus. The energy of the ground state of the hydrogen atom. Okay, so a few different ways, depending on the circumstances, of how you might want to quantify, for ease of calculation, the energy levels, all right, of the hydrogen atom. All right, so let's look at a couple more things just to wrap it up. All right, so then we'll bring it back to emission. The whole point of this last equation is just kind of bring it full circle, and to talk about the idea then of the wavelengths that are emitted by a by a electron that, or by an atom that is relaxing to a lower state. All right, so that's what we have here. So this is for, emission, lambda, and so this is wavelength of emitted light. All right, and we know that this is work that we're talking about emission of light, and of course we're talking about wavelength. It's never electron wavelength, it's always photon wavelength. And we know we're talking about emission because we're going from n final to n initial. Okay, so we're subtracting where n final is larger than n initial. All right, so in this case we can say with n final as, so in other words, n final being a smaller integer than n initial. Okay, so like, n initial could be 5, n final could be 1. So then we'd have 1 minus 1 over 5, which of course is going to give us a positive number because we're talking about emission. Okay? And if we wanted to talk about absorption, then we would just go the other way. Okay? We'd have our final would be smaller, and then our initial would be larger. Okay? All right. So, purpose then of this equation, just to bring it full circle back to where we started with the energy of a photon. Now what about these last three equations? So these last three equations are extensions of the Bohr model. There we are. All right, and so what do we want to say about them? Okay, well, the first one is for hydrogen-like atoms. All right. So first I'll label what Z is. So Z is the number of protons in the nucleus. So number of protons in nucleus. All right, so for hydrogen, Z is just 1, and then we get back to the expression that we derived through the sum of forces and quantifying de Broglie wavelengths, and that worked great. But what if we want to extend this to, say, helium or lithium or beryllium or something, where you have 2, 3, 4 protons in the nucleus respectively? Well, you just plug it in. You just plug in that number, okay? You gotta remember to square it because it's always Z squared. And this only works, however, if those larger elements, those elements with more protons in the nucleus, have lost their extra electrons. Because especially with these smaller electrons, it would be typical to find them in a non-ionized state. I mean, I guess that's kind of, you can sort of think of any basic element as being non-ionized, and especially in a low energy environment. And so that element, it being non-ionized, would then have an equal number of electrons to protons. Okay, it would be electrostatically neutral. But you could ionize it through bringing in some sort of external energy, kicking some of the electrons out. And once you've kicked out all but one electron, then you can use this equation. Okay, but that's definitely the restriction there. So it only works for hydrogen-like electrons or atoms. So for hydrogen-like atoms with only one electron remaining. Electron remaining. All right, so there you go. That's great. Limited utility because, good luck finding something like oxygen that has been so thoroughly ionized it's just got one electron left. I mean, you could sort of pathologically come up with that as an example, but it becomes a little bit of a corner case. So really it's going to be useful for those lighter elements that are closer to hydrogen. Okay, now what about this next one? Well, this next couple equations apply to characteristic X-rays. So let's make that clear if we can. So this is for characteristic X-rays. Okay, so what is a characteristic X-ray? Well, for heavier elements, those ones that you can't imagine them being so fully ionized that they just have one electron left, you can still use the Bohr model if you bombard that atom with high energy electrons, and again refer to lecture 25, and in doing so, shoot in an electron that has just the right amount of kinetic energy, so that when it crashes into the atom, it has an equal energy to the total energy of an electron in the K shell. Okay? Now, I'm not talking much about shells in this lecture at all, but the nomenclature here for characteristic X-rays uses K in the subscript, so I wanted to at least mention that in passing. But the K shell is just the lowest shell. It's just the one that is the only shell that is relevant to hydrogen atoms, because it's where the ground state of the hydrogen atom exists. Okay, so it's where your stable, relaxed hydrogen atom is going to be found in terms of its electrons. But there's always going to be electrons in that shell. Okay, if you want to call it a shell, and if that electron is freed, then that spot is going to get filled back up, and in doing so, there's going to be a release of energy, and that release of energy is going to create a photon. That photon is the X-ray, that characteristic X-ray, okay? And it's an X-ray because it's a very high energy photon, which means it's a very short wavelength, and it's a very high energy photon because we're talking about large atoms. And we're talking about large atoms, thus the energy is going to be really big because the Z is going to be big, so it's going to be that much larger than hydrogen, thus that much shorter in wavelength, okay? And X-rays have much shorter wavelengths than, say, visible light or ultraviolet light, all right? Let alone something like infrared. Okay, so a couple things to label here. Z effective is just the effective atomic number, all right? And number of protons is also called the atomic number, because number of protons defines the atom in terms of the periodic table. It's the most fundamental thing about the atom. The total number of nucleons is going to vary, and that's the idea of isotopes. We'll talk about isotopes later in the next few days. But the real fundamental thing is the number of atoms, okay, or the number of protons in an atom. So so Z effective is going to be the number of protons minus 1, okay? So let's label this right here. So effective atomic number. And the reason that we have an effective atomic number rather than just the straight up atomic number like we used for hydrogen-like atoms is that the hydrogen-like atoms were hydrogen-like. They literally only have a single electron. Well, these are not hydrogen-like. We never said they just have a single electron. We just said that we're freeing one of the electrons in the K shell. Well, that means there's 2 electrons that fit in the K shell. And again, this goes back to the other atomic numbers like spin. But there's 2 electrons that fit in that K shell, which means that if you free one through bombardment, the whole process of electrons, see previous lectures, then there's going to be one left. Well, that one that's left does some shielding, thus we have to take that shielding into account in kind of a roughshod way of subtracting 1. Okay? So effective atomic number. Okay, all right, and Z is still the atomic number, that hasn't changed. And then this is the energy of the electron in the K shell. And the best way to discuss the K shell, but not go down the rabbit hole of talking about all the shells. Again, I go into that in good detail, and there's the slides clearly show all the different labeled shells and kind of why, what that naming means and kind of why we use it. Is that the K shell just corresponds to a principal quantum number of 1, right? So the K shell is just n equals 1. Simple as that, okay? Which is why n doesn't even show up in this expression, because it's just 1, so it's just not there, okay? And otherwise this expression is identical to the energy of n equals 1, so essentially the ground state of the hydrogen atom, right? So good consistency there. All right, so hopefully I've covered everything here in some depth and it all makes sense. I'd say these equations are really the lion's share of what's going on with this set of lecture notes. But let's just jump into a couple of examples to wrap up this video. All right, so there's a couple that I have earmarked to show you, and there's of course some that I will leave. All right, so let's take a look at the first one. This one should be very straightforward. All right, because really using these equations is, as long as you don't get mixed up on what the constants are or anything, it really is mostly plug and chug. I did want to summarize the constants. So before we move on, we're almost ready to do a couple examples to wrap things up. But I wanted to put a little side table in here with all the values of the constants. So m equals me, and I'm just pointing that out because I accidentally used both, right? But every time I talk about the mass, I talk about the mass of the electron. And it's always going to be equal to 9.11 times 10 to the negative 31 kilograms. All right. The fundamental charge E, so every time you see that, that's just equal to 1.602 times 10 to the negative 16 coulombs. All right. The permittivity constant, which shows up quite a bit, is 8.85 times 10 to the negative 12. We'll use farads per meter. We've expressed it other ways, but that's a fine way. Okay. And then we've got Planck's constant, which is an angular momentum quantity, and that one is 6.626 times 10 to the negative 34 joule seconds. All right. We got the speed of light, 3.00 times 10 to the 8 meters per second. And lastly, the Rydberg constant, which we don't need, right? But I did express it. And that's 1.097 times 10 to the 7th. And that one has inverse meters as its units. All right? So there they all are in summary. Some space there. There. All right? And I guess in terms of the sig figs, I know most of them are, well, I'd say half of them are 3, half of them are 4. All the ones that are 3, that don't let that restrict you. Assume that they have 4 levels of 4 numbers of precision, and just the next one is just 0. Okay. All right. So let's just move right on to our first example. Example 1. Determine the wavelength of light emitted when a hydrogen atom makes a transition from 6 to 2. So from the nth state to the 6th state to the 2nd state. Okay, so we have the energy going from 6 to 2. So E6 to E2, and this is emitted, so it's relaxing. So then we should just be able to use this expression. All right, R, and we have 1 over 2 squared, because that's our final state, and our initial state was n equals 6. Okay? So then if we then solve for lambda, that would be the Rydberg constant, so 1.097 times 10 to the 7 inverse meters, and then times 1/4 minus 1/36. Let's see what that is. All right, so 1 over 4 minus 1 over 36, because 6 squared, of course, is 36. So 2/9. Okay, so it'll be 2/9. All right, and then that whole thing has to be raised to the -1 power, because that's the way I was able to get lambda by itself. All right, just take its reciprocal. And so then that ends up being 4.10 times 10 to the negative 7th meters, all right, which is our answer. But we could express that in terms of nanometers, which would be helpful for comparing that to visible light, or where it is, because it turns out it actually is visible. So 410 nanometers, that tells us that this is sort of bluish light, right? So it's visible light on the blue side. All right, it looks good. All right, so let's take a look at another example. So I wanted to look at this one. So consider the Bohr model for the hydrogen atom in its fourth excited state. Determine the binding energy of the electron. That's part A. Part B, what is the radius of the electron and how far is the distance to the next higher excited state? Okay. All right. So to find the binding energy, we need to find out sort of what is its total energy in the fourth state, and then subtract that energy compared to the ground state. Okay, so what's the best way of thinking about this? So trying to think about kind of the best way to express this. So we have, because we can find out how much energy we have here. Determine the binding energy. That's how much the atom is holding on to the electron. Just trying to think about the conceptual meaning of it. Because if we take, because the total energy, and then sort of thinking about that relative to the idea of it being bound. So let me write this out, and then I think I'll collect my thoughts on this. So I have, so the binding energy is going to be E1, so the ground state energy, minus the value of E4. And it's got to be minus the magnitude of the value of E4. So let's think about what's going on here, because it's the total energy. If we added the energies together, so let's think, because if the electron is freed, if it's ionized, and its total energy becomes 0. And I think that's the key idea here. So I have here, it's minus En. Okay? So that is the expression for the binding energy. It's the ground state energy minus the magnitude of the nth energy, the total energy, right? Not just the potential, but the sum of the kinetic and the potential. And if the sum of the kinetic and potential energy is 0, then we have an ionized atom. So let's think about this then. Okay, so this is as deep in the well as we can go. In this case, as we go up to higher energy states, such as the fourth, we're less deep in the well. We're approaching freedom, all right? And the minimum freedom is 0 total energy. And so if I'm talking about it being bound, that's kind of how much. It's just kind of, I guess it's the terminology that's throwing me off here. It's like, why are we calling this the binding energy? It's how much the atom is, because it's not how much the atom is still holding onto it so much. Well, I don't want to overthink the terminology. We'll just kind of leave it there and say, okay, this is our expression for the terminology, and we're okay. All right. So I think probably the best way we would write this then would be, we have then the 13.6 electron volts, and then minus our 13.6 electron volts divided by n squared. Okay? And again, because we took the magnitude, that's why it was a minus, it didn't become a plus. Let me make sure I wrote that correctly. Yep. All right. And then so in this case, so thus we can say E binding will just be 13.6 minus 13.6 divided by 4 squared, or 16. All right, so then we just would have 1 minus 1 over 16 times 13.6 electron volts by factoring out the common 13.6, putting it at the end. All right. And so then that's going to be, let's see what 15 sixteenths times 13.6 gives us. Gives us 12.7, all right, or 12.8 if we're rounding to 3 sig figs. So 12.8 electron volts. All right. So yeah, I mean that's not the total energy of the fourth state, but that's the difference between the two energies. Or that's what the bindings represent. It's the difference between the two energies. Okay? Looks good. Okay, and then we're asked for the radius. Okay, so that one's pretty straightforward. So R for n equals 4 is R4, and that's just going to be n, well, it's just going to be, so here, right, first of all, Rn is n squared times the ground state energy. So here, I should say Rn, excuse me, Rn. So here, R4 is going to be 4 squared times our Bohr radius, which I haven't given you a numerical value for. So let's go ahead and work that out. So our Bohr radius is, so we have, let me copy it over here. So I have to flip back and forth. So let's take a screenshot of that. Okay. Okay. And so then that will be 4 squared, so times permittivity. So we get all our constants in here. So we've got our 8.85 times 10 to the negative 12 farads per meter, and then times Planck's constant squared, so 6.626 times 10 to the negative 34 joule seconds, quantity squared. And then we have to deal with the denominator. So pi, mass of the electron, so 9.11 times 10 to the negative 31 kilograms. And then the fundamental charge, 1.602 times 10 to the negative 19 coulombs, square it. Right, more obvious. Okay, let's clean this up a little bit. Okay. All right, and then this whole part here, we'll get a numerical value for that, and that's going to be our value for A naught, the ground state radius. Okay. So this whole thing is A naught, and it should be equal to, let's see, 5.29 times 10 to the negative 11 meters. 29 times 10 to the negative 11 meters. There we have it. Okay. So that's our tightest radius, smallest one. And so in the fourth state, it's going to be 16 times bigger than that, and that ends up being 8.46 times 10 to the negative 10 meters. Right, so over an order of magnitude larger. Looks good. And in the last step, we're asked for how far is the distance to the next higher excited state. All right, so that would be n of 5. So that should be R, so our delta R, I should say, in this case would be R5 minus R4, which would then just be 25, because that's 5 squared, minus 16 times A naught, right? And we know that A naught is numerically 5.29 times 10 to the negative 11 meters. Okay, and so then our distance is 4.76 times 10 to the negative 10 meters. Right, so it's pretty far to the next highest step, right? So these orbits are getting, you know, much more spread out as we go. Okay? All right. We didn't quite double it, but we had to go half again as far, which was a much bigger step than, say, if the difference between the say the third and the fourth radii. Okay. All right. So hopefully it all makes sense, despite my little confusion there with the binding energy. Just terminology I don't use too much, but I know was used in this problem, and I wanted to use it. Okay. All right. So I have 2 more I want to show you. So I'm leaving 3 and 4 for practice, and now I want to show you 5. Okay. So please complete 2 and 3 if you're looking for extra practice. Example 5. If the energy for the ground state of hydrogen is negative 13.6 electron volts, which of the following gives an approximate value for the energy of electron of the K shell of the element beryllium for which the atomic number is 4? Okay? All right. So we want to not talk about hydrogen-like beryllium. So this isn't triply ionized beryllium. This is just normal beryllium. And so since this is normal beryllium, we're using the characteristic X-ray formula. All right? So we could say that this electron energy is related to characteristic X-rays. In this case, we're not producing one. We're just talking about the energy of the electron. Okay, but that could be a follow-up question, for example. All right, so then we're just going to use the expression of the Z effective. So then we'd have EK for the K shell is then going to be negative Z effective squared. And then here, let me actually copy it over so I don't have to write it out. So this will be our expression. Okay, oh, there we are. All right. Get that in there. All right, and now let's go ahead and just start plugging in the numbers. So Z effective in this case is going to be 4 minus 1, because beryllium has an atomic number of 4 because it has 4 protons. It is the 4th lightest element because we got hydrogen, helium, lithium, beryllium. It's going to be squared. And then we'll have our mass of the electron, 10 to the negative 31 kilograms. All right, then our fundamental charge, 2 times 10 to the negative 19 coulombs. We've got to raise it to the 4th power here, right, as we do with all the energy expressions, if we're expressing them in terms of these values, not using like the Rydberg constant, for example. Then we'll take our permittivity constant. So that was 8.85. Not forget to square it. Times 10 to the negative 12 farads per meter. Okay. And then times 8 times a n of 1. All right. Oh, I think I might have said that, oh, here, we don't have to worry. This is specifically for n of 1. Let me look at my notes on that. Yeah. So for the K shell, it's going to be an n of 1. And I know n is left in here. And then we have, yes, yeah. So the idea is that if we did want to talk about expressions for other than the K, then we could put in the other n values. And that really would be relevant only for having that shell filled. So if I wanted to assume that I was talking about the K alpha line, again, refer to the figure that shows characteristic X-rays. So the K alpha line is filling the K shell from the L shell. In that case, you're filling it from n equals 2 to n equals 1. So we'd use the same expression for n equals 2, then use it for n equals 1, find the difference, and then find the wavelength that corresponds to that difference in energy, the photon wavelength, of course. Okay? But here we only care about the electron, and so we'll just have an n of 1. Okay? Because we're in the K shell. And then Planck's constant, 6.626 times 10 to the negative 34 joule seconds squared. All right. So now, here's the thing, right? So this whole business here is actually going to be 13.6 electron volts. So then I could rewrite this as negative 3 squared times 13.6 electron volts. All right. And then, see, so that's just 9 times 13.6. Okay, and you might be like, what? You might be like, why did I bother to even write all this if I was just going to say that it's electron volts? Well, I just wanted to kind of go over the values, right? But that is 13.6 electron volts because it specifically is n of 1. Okay, and so that gives us the total energy of this electron is 122 electron volts, negative 122 electron volts. Now, it's larger because it's more tightly bound to the nucleus, right? It's deeper in the potential energy well, right? This electron would have to gain a lot more energy to be ionized. It's much harder to ionize it, right? Now, it's maybe not, we didn't square, it's not 16 times bigger because there's another electron that's partially shielding the nucleus, all right? But it is still, has more negative energy, more tightly bound. The other thing we could do is convert it over to joules, in which case we would just multiply by 1.602 times 10 to the negative 19. And so that gives us that this is negative 1.96 times 10 to the negative 17 joules, because there is 1.602 times 10 to the negative 19 electron volts per joule. Or joules per electron volt, excuse me. There's there's the reciprocal of that, but that's how many joules there are per electron volt. Electron volt is a very small portion of a single joule. All right, good. Last one. All right, and this one I wanted to actually talk about something that was hydrogen-like rather than non-hydrogen-like. An atom of doubly ionized lithium is in an excited state. What is the principal quantum number of this energy state if the energy is completely ionize this atom is closest in value to the energy to ionize a hydrogen atom in the ground state? All right, so we're just going to find the closest n that makes this work. Okay, so first of all, what I want to find here is I want to consider, let's see, because we're going to, so we know that the energy to completely ionize, that's it, we just want to collect our thoughts here. The energy to completely ionize a hydrogen atom in its ground state is how much? 13.6 electron volts. So the energy to ionize hydrogen in n equals 1 state. If it's already excited, it would take less energy, a smaller input. But if it's totally relaxed in its ground state, then it would take a one-time input of 13.6 electron volts to free that electron, which means it's kicked out, no longer can detect a nucleus because it's too far away, and it's got no leftover energy, so it's kicked out and it rests somewhere. Of course, good luck getting an electron at rest. It's going to go somewhere else, right? But this is the theoretical idea. Okay, so the energy to ionize hydrogen equals up is 13.6. Okay, so that means that, so then we want to set En equal to 13.6 electron volts, where En is going to have the expression of Z. Okay, so then we're going to have negative, and here, since this is the energy input, we're not going to have the negative because we're not talking about the total energy of the electron. We're talking about the energy it takes to go in, which is just the negative of the energy of the electron. And so then we'd have Z squared, and then times the expression. Okay, so then it's just going to be m e to the fourth, and then divided by, we've got permittivity squared times 8n squared h squared. So 8n squared h squared. Okay? So then I just want to find the n that's going to get closest to that value. So the best way to think about this is be like, okay, well, this whole expression is only different by the z squared, right? And so that means that we should be able to pull out the z and the n, right? So then this should look like this. It should then be z squared over n squared times 13.6 electron volts. Okay? So what's that, you know, what are we looking at here then? Okay? Well, let's first of all confirm that that's correct. Okay? So then I just want to confirm that this expression with an n equals 1 gives us our ground state energy. Okay? So we're just going to go back over to the expression for energy, right? And so we have En, right? Well, here it is without R. Okay, so m e to the fourth, permittivity squared, 8 h squared, okay? If n equals 1. Okay, so, yep. I mean, well, yeah, I mean, there's the n, okay? So we're good. So then, we just want to solve for n. So thus, we would have 13.6 electron volts equals z squared over n squared times 13.6 electron volts with z, well, we're talking about lithium, so z is what? 3. Okay? Obviously, the 13.6 cancels. Okay, it just becomes 1. And so then we're just left with then z, or we'll have n squared equals 3 squared. Oh, just n equals 3. All right? And it ends up being exact, right? So in other words, when you have a electron in the third energy state, the third excited state of lithium, it has the same total energy as an electron in the ground state of hydrogen. All right? Now, is it exact? No, because there's some things we're not accounting for here. Okay? First of all, there's more energy states now, and there's, if we consider other quantum numbers, and there's some other effects. It turns out there's something called the corrected mass. The bigger mass of the proton of the nucleus, because there's not just one proton in there, changes the dynamics a bit. So it has some important corrections. So those are some further corrections that make the values become less and less accurate. But they'd be pretty close. All right? All right. So that's our final answer. N equals 3 would be the excited state. Yep. Because that's where we were solving for. All right. So that concludes this lecture. Thank you so much for watching, and please stay tuned for the last few lectures where we talk about nuclear physics and nuclear energy.